Thank you for inviting me, and I will start right away with the presentation. It's related to the research project that I am involved called Recreate, which is based for reusing concrete for a circular economy. And the presentation is titled Frameworks, Digital Tools, and Climate Benefits of Concrete Reuse in New Buildings. We know that the built environment is responsible for a large share of global CO2 emissions, as well as almost half of all extracted raw materials. And further, this is expected that the building stock will double by 2060. And also, material usage is expected to grow. At the same time, buildings sometimes have a much shorter lifespan, and like in this case of the Kingdom in Seattle, as well as even if we demolish, it does not come without impacts. It's expensive. There's environmental pollution risks, and it's time consuming. So could we do better than currently? And why are we focusing on concrete? Because concrete is and cement, where most of CO2 emissions from concrete are almost responsible around 7 to 8 global greenhouse gas emissions. And if we look at the circular economy, and also the waste hierarchy of the European Union, it argues first for prevention and then for repairing and reusing of the existing products and of the existing building stock. And then we can look at other solutions like recycling or other forms of recovery. Based on the waste hierarchy, the focus on Recreate is on reusing, and we are looking at precast concrete buildings. And the idea is to reuse the whole elements, the walls, the slabs, as they are in new building projects. And these are some form models of the different pilots, deconstruction pilots of the 4 countries involved: Netherlands, Germany, Finland, and Sweden. When we look at the reusing structural concrete, right now we don't have there are some databases coming up, but initially it starts. Design is the last step, and the first step is identifying elements or components either through a database or in the existing building stocks, buildings that will be planned for demolition, and gathering as much possible documentation that we can that exists out there, or gathering this through scan to beam approaches, machine learning, and conducting laboratory tests or non-destructive tests to guarantee the quality of these materials. At the same time, we want to know where these materials come from and where they are going. So we also are looking at digital technologies for tracking and tracing these elements and where they will be located in a new building, and possibly if they will have further life cycles. And then when we are designing with reused elements, there are different tools that could help to have a database, to have workflows that could analyze the building performance, the lifespan of elements, and embodied carbon and circularity. And we are addressing some of these elements in my research, but more comprehensively across Recreate with the other partners. So I will look at some of our recent publications on data and models, so looking at BIM standards and frameworks, and the logistics, and on the quality assurance and environmental benefits and impacts. And also circularity and pre-deconstruction are aspects of interest, but they are less the focus of this presentation. The area that we're working on is in Helsingborg, south of Sweden. And it's called Drottninghög, which was built in the 60s, during the 60s and 70s in Sweden, they built around 1 million apartment units for housing. And they were very ambitious and used prefabrication techniques and mostly concrete at the time. Now these buildings are in need of refurbishment, and in some cases they are planning to densify and to also diversify the offer of apartments. So some of these buildings will be either deconstructed, and we have done a smaller pilot, and we are also planning to do a larger pilot in the area based on deconstruction and reuse of these elements. I will go through 4 of our publications, and the first 2 publications were conferences where we looked at the level of information need and to propose some guidelines for use. for concrete. And the second paper is on reviewing tracking tags and proposing a workflow and testing these on precast concrete elements. Since this is a BIM conference, I guess you are all familiar with the concepts of level of definition and level of development. And we are moving from that approach towards a level of information need, where we define purpose, milestone, actor, and object, and also define what should be the information in terms of geometrical, alphanumerical, and documentation. And this is also being developed. It just came out as an ISO standard. It came first as a European standard, but now it's also an ISO. And these are complementary but also independent metrics for quantifying the information needs. And also one purpose of it is to prevent too much information. I will quickly go through what we looked in the paper. So in the European standard, there is a diagram on this prerequisite and level of information need, and what we discussed in the manuscript was looking at what does this mean in the context of reusing concrete, the purpose, the milestone, the actors, and the object, and also defining what should be the geometrical information, discussing it, and or alphanumerical, and the documentation that's involved in the concrete reuse. Without too much further ado, just to give a quick example, for example, the standard in the location in the standard describe the position and orientation of the object, and this is something that it's still important for concrete because we want to use a wall as a wall, a slab as a slab. Usually, if we are using the whole element and not just the concrete block, so this is an important aspect. But at the same time, reuse also entails expanding the level of information in the framework, because we need to know where the address of the donor building or the production factory, to know the type of concrete that was used, aspects involving the deconstruction that could facilitate and store it into BIM, and also connected with the tracking tags, material passports, and sharing in a database. We also, in this work, we also compared the different modeling strategies in Revit in support of sharing these elements or the capabilities based on that. And the modeling in Revit is quite limited, and it would tick some of the boxes for the level of information needs standards, but some other modeling strategies it would not tick some other boxes. And the only modeling strategy in Revit that would tick more of the boxes, it would be the sort of a workaround that would be the model in place to save the elements as a group, and then we could perhaps you could load those as elements, the walls or the slabs, which are native families in Revit, and it would be, and all the other strategies would come with some limitation. And for example, after we also look at Rhino, and even Rhino, although it's not a BIM tool, it's a CAD tool, it would tick most of the boxes for the level of information need frameworks. So modeling sometimes in these proprietary tools comes with quite some limitation, and it's not so possible to switch easily between those modeling strategies in Revit. But when we look at circular construction, we need to share these elements because they need to flow from one donor building to another building, or from one BIM model to another. In this study, we didn't look at the Blender, but that's also another tool that's interesting because you can draw natively in IFC. And then on the next study, we looked at tracking and tracing elements. So tracking is following the path forward, and tracing is knowing previous information and where the elements are coming from. And it could be useful for knowing on the previous life cycles of the element, or for calculating some modules for life cycle assessment, like transport, through the tracking tags, and also knowing the lifespan of the elements. There are several technologies, and usually we make a very brief comparison of those. And usually the literature has focused on radio frequency identification, while these other technologies like NFC, which is a subset of RFID, which is available in credit cards in our smartphones, has not yet been used as a tracking tag. And this was something also, these recent developments on Bluetooth tags, which are widely used for decentralized tracking or QR codes, were of interest. And we can see that RFID, mainly the focus on the research has been on that, while the other technologies, it would be harder to locate within this. Here I can see Bluetooth, and perhaps there will be also QR code somewhere. So the idea is to connect these physical elements with a database or a material passport and in the BIM application to facilitate the identification and reuse of the elements. In the paper, we also propose the workflow. So the text could be either a property of elements, but could be also, for example, we propose a face-based Revit family for modeling, which could facilitate the location where these elements are placed through a digital model. Because these tags are sometimes not easily accessible or findable, but if we include them in a digital model, we may more easily know where these are located, especially if they are short range tracking elements. So in this case, it was not just looking at one type of tag, but also exploring the different possibilities or combining these different tags along the life cycle of concrete elements, depending on which surface is exposed and which is covered, and looking at the potential benefits of each. We propose a workflow for tagging or for storing through the information in the tags with Speckle or through a Microsoft list, and then connecting this with a BIM model and copying this information in the BIM. We did different tests, as I explained by embedding inside the NFC chip or locating it in the surface, or by combining it with a Bluetooth tag in the paper in case the Bluetooth is used to track elements during transportation and for decentralized tracking through mobile phones. And we had some positive reading even when the NFC is embedded into concrete. You can have reading, although it's a short range, and also QR codes for reading the element, the naming convention, the element, what element it is, or by accessing the database. The readings for different attachments of the NFC were quite positive, except for the last scenario where we used the hardwood floor that was 2 centimeters thick or more, and when it was embedded into concrete. The following paper looked at it was a journal paper that looked at the comparison of digital tools for a circular economy and the CAD, BIM, and computational design plugins. It was focused on possibilities and limitations of these tools. And what we find, so this is like it's composed of 2 parts. One part is making a bibliometric analysis of the literature in the past years on the topic of circular economy and digital tools, and also on looking at the databases that have different plugins. And what we find is that there's now, I don't know if you can see, or it's the bar of my window screen, but the number of publications is increasing over time, and also the methods used for circular economy research on circularity is increasing from CAD, BIM, geographic information systems, or a combination of tools, including computational design. And what we looked at them in this bibliometric analysis, it's that after circular economy, BIM was the second most used keyword and most focused topic relating to circular economy, followed by LCA, sustainability, construction, and so on. And reuse was actually a bit lower, on 9th, but still it's quite an important. And then there's all the list of other keywords that were emerging in this analysis. Then through bibliometric analysis, we also found different countries, which countries had conducted more research and had more citations, and also the comparison of various features of these different tools. So in case what we found is that LCA is the most used assessment framework, and also there were a variety of BIM tools automate this analysis of LCA, but at the same time they are less flexible than computational design plugins. And another aspect was that these tools, for example, don't integrate only one database for life cycle assessment, but depending on the region, you necessitate another database. So that's a limitation, but that can be more easily overcome through the combination of computational design workflows. And what we found that beyond LCA, there were also a lot of digital tools on computational design, and also we found some gap that there were a lot of these computational tools on designing through a stock of reclaimed for example, linear elements like beams, like wooden beams and so on, but fewer design tools are designed for supporting the design for concrete. And then the second paper that I will try to briefly go through is where we propose a digital tool for concrete and on circular economy. And there's been some recent over the past years seminal research saying that concrete is a carbon sink, and also other proponents that concrete should not be considered a carbon sink. And there are different roadmaps that aim to decarbonize concrete, and they look at different aspects, so optimizing material efficiency, using less concrete and so on, or using the existing structures, or carbonation at the end of life. But in this, but the reuse of the buildings or of the concrete elements has been less, not has paid less attention in the literature. And when we look at concrete in, for example, in service life predictions, the main aspects that concern durability are either carbonation or chlorides, and usually for buildings or for facades can be more carbonation. And this service life prediction is divided into two steps: the initiation phase, so how much time does the CO2 or the chlorides need to arrive at the reinforcement, and they could potentially depacify the protecting layer of the steel, and then the steel would start to corrode, and this would either lead to cracking or to spalling over time. And I will briefly go through this. So carbonation is this natural process where concrete recaptures some of the CO2 that was emitted during calcination, during the production of cement, and also the reactions for chlorides. But I will go forward, and there's been some research that looked at the carbonation of the concrete cover, which may lead to depassivation, corrosion, and damage, but not necessarily to this aspect that would reduce the service life and durability of concrete. So, and it was interesting for us to look at what it means in the context of reuse. And there is also research that carbonation does not lead to widespread damage in buildings, but it's still something that we need to consider and to look at if it's more beneficial than reusing or not. So we propose this digital tool to determine the service life by carbonation depth, the initiation phase, and to calculate the CO2 uptake in concrete through digital models. And also to compare this or to calculate a more comprehensive embodied carbon of concrete with databases. And in this case, we use Swedish databases. So due to brevity, I will not go in detail into the calculation methods, but you can also look into the paper. There's a standard on how to, for environmental product declarations, on how to calculate CO2 uptake in concrete by carbonation, and also a technical report that is related to the standard. We rely on the square root of time model for the simplified model, which is a generally acceptable model for concrete service life and CO2 uptake, which has been widely used in the literature and also validated by previous research. And we look at different life cycles model product, construction, CO2 uptake during the use stage. And at end of life, we don't look at impacts of deconstruction, transportation, or disposal, but only of processing. If the concrete is stored prior to reuse, or if it's crushed, and we try to maximize uptake for recycling of it. And for module D, we look at the lifespan, CO2 uptake potential, and theoretical carbonation. We did the tests in Recreate, but we also looked at the various more recent studies in the literature that had provided carbonation rates, and the European standard on EPDs provides quite some high numbers for carbonation, and we looked at what this means, and also the databases that we used. Without going into much detail, we used the average data for precast concrete products in Sweden, which is available through an API, and this is provided by the Swedish National Board of Housing, and this includes only modules A1, A5. So this is why, and now in the workflow, only these modules are included in the digital tool, but we could include further modules when information about other life cycle stages is available. We propose a way to estimate if a building is planned for demolition and two levels of assessment. So to calculate lifespan and carbonation on these concrete elements, and if the remaining service life, the initiation phase of these elements is greater than the service life of a recipient structure, you can reuse them. But if not, there's further considerations that need to be done. So if there's presence of corrosion, if there's a necessary reconditioning of the elements, or perhaps using them in lower story structures and for shorter lifespan structures. So this is what it looks like we got a B model and connected it to Rhino and Grasshopper to make the calculations for lifespan. And we also made an assessment through drawings and through ground penetrating radar to estimate, to verify if the concrete cover was the same as what we found in the drawings. And it was mainly correct. The slight variations are due to the differences in materials of the different surfaces in the floor. So these are floor plans of an apartment that we scanned. And also we mapped concrete conductance to look at which parts of the concrete could be more exposed to humidity or to ions that could potentially depassivate and lead to corrosion. And of course, there's perhaps more moisture content. There were higher values in the bathroom. So these elements may need to be checked before used. And we also found highly uncarbonated concrete when we did these partial drills on the elements. We found that by using on the upper table, by using the values provided in the standard, the elements would not be deemed reusable because the service life, the initiation phase would have been consumed. But if we use this more recent data from Recreate and from the literature applied to the case study, we found that all those elements would be reusable and there would still be some uncarbonated concrete cover. But even if it was carbonated, the elements could still be reused indoors because it's the presence of moisture and oxygen that would lead to depassivation and corrosion. Then we also compared these results with these different life cycle stages and carbonation during use or during reuse or recycling, and also the theoretical uptake with embodied carbon. And mainly if we consider all the theoretical uptake, that's around 21% of the embodied carbon. But if we look at only the uptake that could be achieved through the first and second life cycle, that's not more than 6% of the embodied carbon of concrete. So it's still a considerable number, but it's not too high. The proposed approach in the paper could also be used to design for use. So by considering if we need to extend the service life of elements to match them with the new recipient building, we could look at different strategies to extend their service life by protecting the elements, perhaps if they are used outdoors with a hydrophobic coating from moisture and water, or if they are used indoors, perhaps to use plasters and coverings that would further reduce the carbonation rate. And that's something that has been extensively shown in the literature in case of bridges or buildings where they found very low carbonation rates due to dense plaster supply or coating supplied to concrete. We also made a life cycle comparison of these emissions, and as we can see, the emissions that are realized during the life cycle, the first or the second demolition or new build, or if we reuse the concrete, carbonation is like very little and does not have a decisive influence in this case. And the lighter purple color is the theoretical uptake, what has been remained, which is not realized even through two life cycles, but that number remains there and is presented in a less life cycle. And if the concrete is reused more times, then this number gets reduced, and it should always be reported in the last life cycle. We've found some interesting findings when we used these different allocation approaches. And since carbonation is greater in the first years due to the square root of time model, if we use the 50-50 distributed allocation, then embodied impacts, including carbonation, are slightly higher in the second life cycle than in the first life cycle. If you look at this number 117 or 122 or 200 and 203. But at the same time, if we just look at the second life cycle, which is what people in practice would do, if we a new building would have slightly lower embodied carbon than for the concrete than than a reuse project with the end of life allocation, because end of life allocates the embodied impacts in the second life cycle plus the carbonation of the second life, which is lower than what is in the first. So it would lead sort of to these contradictory results that it's better to build new. So the end of life allocation is not recommendable when including carbonation in the results. The cutoff allocation, as we can see, is the most beneficial for using of the existing stock, and especially if we include also carbonation, which gives a very low embodied carbon at 7 kilograms of CO2 per square meter. In the paper, we also show a circular construction concept for concrete. So we can first is resource efficiency, so narrowing flows. And closing flows, it could be done even through recycling. And a great deal of research has looked at service life extension, so reconditioning of concrete and repair. And if we do both, like service life extension and reusing the concrete, we are sort of applying all the possible circular strategies to concrete. And based on this framework, narrowing, closing, and slowing. So key takeaways from this paper is that the current carbonation rates in standard prevent reuse. I may as well overestimate carbonation. And this carbonation, it's actually something that happens throughout the lifetime of elements, and it would be better calculated than weighed than in a standard way through product declarations. And this is something they need to factor in the design because the actual conditions may change in the future building. And this is also useful for reporting concrete carbon, this workflow and these updated carbonation rates for reporting carbonation through the IPCC guidelines, which haven't been updated since 2006, but it could be useful. And this is also useful also for LCA, because we usually take for granted in an LCA that the structure is there for 50 or 60 years. But if we are using elements, we perhaps need to incorporate this more comprehensive way to look at that elements may have different lifespans and matching them and to be more considerate, especially when we are using them as structural components. And this is also addressing a RILEM recommendation for these carbonation rates that need to be updated to be valid for service life and for CO2 uptake. So I think I was on time with the presentation, and I'd like also to thank my collaborators, Kjartan, Tove, Jose, Ariana, and Johan, that have also collaborated in these studies with me. And thank you, and please reach out if you have any questions.